So in my ongoing discussion with Paul Gradenwitz, I want to make sort of a description of something of a global nature and a local nature. Um, I was saying if we have a process coming from inside a gravity well, and let's let's give a graphical description of this. Gravitational potential versus radius, and radius being I drew that circle down there, but I'll just erase this circle right for now. Gravitational potential versus radius. And this thing will be of a form, actually it goes to negative infinity as you go to zero, but really there's going to be a cutoff if the material is a solid. And actually that won't go down that way because within the thing we'll get into a within the object, if it's kind of a fluid or something like that, we'd have to change that formula for gravitational potential. But anyway, it's basically a cutoff of gravitational potential energy is mg over r. Is that right? Uh, negative mg over r. Gravitational potential energy goes negative mg over r. And I'll just use absolute value sign of r there so that it comes down this way here, it comes back up that way there. That absolute value sign is because we're describing it in a coordinate system that goes with r both left and right. Ordinarily you'd have radius just go from 0 to infinity and you wouldn't need that absolute value. And I'm saying that if we have something which creates a change in the speed of time down here, well, if that has an effect on the speed of the clock down here, and let's call it del tau del t at r equals constant. So it's and the tau is the duration as the clock goes. The t is the duration as the actual coordinate time goes. Now this is something that can be calculated from the Schwarzschild metric, at least not necessarily 100% accurately, but at least as an approximation. Here's the Schwarzschild metric, and what I'm going to be doing is setting every term that has constant to 0. So saying r equals constant means that dr squared, dr is 0. So this is multiplied by 0, cancels out. We can also say, we'll also consider something that is coming straight out. So theta is constant, so d theta is 0, and d phi is 0. We're not coming around. We're imagining a photon, or we're imagining, well, a particle that is sitting at a constant space on the surface. So could also imagine a particle that is sitting on a rotating surface. In that case, d theta would be non-zero, or d phi would be non-zero. We could imagine a particle going in circles, or like on a rotating surface if we wanted to put dphi in there. But anyway, for now, we just look at this part of it and we calculate that dtau squared over dt squared equals, we'll have c squared 1 minus r sub s over r, and the c squared cancels with the c squared, and so this is what we have. So taking the square root of both sides, d tau over dt with r comma theta comma phi constant is equal to square root of 1 minus r sub s over r. The Schwarzschild radius. The Schwarzschild radius is 2 times the universal gravitational constant times mass divided by c squared. So we can replace that with 1 minus 2gm over rc squared. So this is essentially the period of any process compared to how that period is observed from outside of the gravitational well. Now, as far as the approximation goes, I think this is probably a pretty good approximation as long as you are well outside the event horizon. The closer you get to the event horizon, which is that number there, the worse that approximation actually goes. And I'm actually not talking about math that I've really done yet. I'm talking about math that I probably should do. I don't have time, or I'm not thinking about it right now, and that's maybe a character flaw, but sometimes I want to just continue discussing things even though I don't have time to do the math of an idea that comes to me while I'm talking about that. But just to make it more clear, let's talk about what I do trust rather than what I don't trust, is that I think this formula is roughly accurate when it comes to situations where the radius is much, much greater than r sub s equals 2gm over c squared. I think that this has been confirmed um, has been essentially confirmed by situations with radio telescopes, not radio telescopes, but GPS systems and stuff like that. I think this is at least as an approximation, it's turned out to be a good approximation for the scale of time on the surface of the Earth compared to, say, the divided by the time on at a further away from the Earth. And it would go dtau at r sub 2 divided by dtau at r sub 1 equals square root of 1 minus 2gm over r sub 2 c squared divided by square root of 1 minus 2gm over r sub 1 c squared. And of course, if r sub 2 is infinity, as you would get if you were completely, or if if this one was r sub infinity, you would basically get 1 down here. 1 minus something over infinity is 0. So I said there might be some local change in the wavelength due to refraction, but once the wave gets out into space, it's all based on the frequency and the speed of light. So here, question is, there's going to be some change, and I'm talking about, say, dr dt. Well, my model of the situation is that the speed of light is changing in this region. How can I describe that? Well, in fact, that's what I mean by refraction. Whoops. Okay. Refraction is sort of n equals the speed of light in a vacuum. The index of refraction is the speed of light in a vacuum divided by the speed of light in the substance. Now, this has no effect. N does not appear in this equation. We're not going to have an index of refraction in that equation. Where we're going to have an N is in figuring out, from the point of view of an external observer, somebody that is outside the gravitational well, that photon is going to be moving a little bit slower here, and it comes out and it's going faster out here. And it comes fairly quickly to very close to its maximum speed as the difference between this quantity 2gm over rc squared. As that approaches 0, as r gets large compared to 2gm over c squared, then this whole quantity approaches 0. As a matter of fact, you can get um, an exact measure of what is the speed of light for this photon coming out using the Schwarzschild metric. Let's do that, while I'm thinking about it. All we got to do with the Schwarzschild metric is plug in, well, we want dr dt. This is the speed. This will be the speed in the kind of looking in coordinate system, dr dt, but in this case, our it's del r del t. It's a partial derivative, but the thing about the partial derivative here is that we're going to be setting tau equals 0, dtau equals 0. We want to consider a situation. I don't know if we need to say tau is 0, but we do need to say dtau is 0 because we're considering a situation where because a photon does not age. It's called the null. I guess it's called the null geodesic. It's the path on which the clocks do not age. So this part goes away. We're also going to say that dtheta is 0 because we want to consider a particle that is just moving straight out of the wave, straight out of the gravitational well. So dphi equals 0. And so what we're going to do is just take this part and cancel those out. So we will just have dr dt equals, so I'll be pulling that one down and pulling that down, and we'll have 1 minus r sub s over r. I'll go ahead and square it so that I can do this in 2 steps. 1 minus r sub s over r times c squared divided by 1 minus r sub s over r to the negative 1. So basically 1 minus r sub s over r squared c squared. And taking the square root, we'll have dr dt equals 1 minus r sub s over r times c. So that means that the speed of light is slowed from the outside perspective by just a small amount, 1 minus 2gm over c squared. So, whoops, forgot my r. Okay. 1 minus 2gm over rc squared is this times c. So this is a slowing of the speed of light, which is pretty much in every way analogous. It's analogous to refraction because it just slows the speed of light. N equals n of the substance, and here we're talking about a sort of a substance that's local to the gravitational well of where the object is the body, the masses, and over n of the vacuum, or I'm sorry, speed of light in the substance divided by speed of light in the vacuum, and that is going to be dr at r compared to dr dt, dt at, divided by dr at r equals, I'm sorry, okay, dr dt at r equals r to dr dt at r equals infinity. So it just comes out to be 1 minus 2 gm over rc squared. And because the c because this will be just c. Okay. Now my feeling is that's all we need. We don't need to additionally how do you say reduce, cut down, chop down the length. We don't have to make any modifications to the length here. This is dr dt. This is the x. Both are basically the Euclidean r coordinate and the Euclidean time coordinate. I know they technically Euclid didn't discuss time, but so having looked at that, let's look at this next statement by Paul here. You would have a change of frequency climbing the gravity well, and then constant wavelength all the way to the observer. Would you have a change in frequency? Well, in some sense, you would have tau equaled here is a little bit different, and the tau or del tau del t at r equals constant would be different there, because you're at different r's. But what? But yeah, that I already covered. It is over here. Del tau del t. No, it's right here. Del tau r sub 2 divided by del tau r sub 1. So wherever you are on this, in whatever radius 2 you're at, you're going to have a different measure of the frequency or the period of the thing. But once you get out into free space, it's more or less a constant del tau del t, because the t is basically what tau would be at r equals infinity. And then you'd have constant wavelength all the way to the observer. And I think I agree with that too. Do I have a calculation of the wavelength? I don't think that I did any math. Del r del t. Now this was a calculation of the speed. So let's think about the wavelength for a little bit. And I think in order to do that, I really need to set ds. We need to take the time-like formula, or the space-like formulation of this, which is essentially the same, except, and we're going to once again just eliminate the theta and the phi and just look at the radial part, but it's going to be dr squared times 1 minus r sub s over r inverse minus 1 minus r sub s over r c squared dt squared. And this time, we're not going to set ds equal to 0. This is going to be our ruler measure. This is going to be the this would be the local description of the wavelength. As a matter of fact, it's not even going to be a differential. It's going to be lambda squared equals, and this is going to be the wavelength in free space. This is going to be lambda space. We'll call this lambda sub naught. This is the, or no, we'll call this lambda source. Lambda. And then this is a little bit tricky because I've got, well, basically the wavelength is described by two simultaneous events at two different locations, which would suggest that dt equals 0, which means those two events are simultaneous. So in final form, if we make that 0, lambda over lambda sub naught equals, I'm sorry, lambda the source, lambda observed over lambda at the source is going to be 1 minus r sub s over r. So in my next video, I think I'm going to be analyzing this result and seeing if it is consistent or inconsistent with my previous result and whether this is overdetermined or whatever. Thanks for watching.